Okay, for this problem, first question I have for you is this would be called a steady state problem. Why is that the case? This is steady state because it could continue like this forever. As long as the steam continues to show up at the inlet and at the outlet as it is, it'll run forever. It's not like it's filling up. It's not a bucket that's filling up with something. So that's why it's called steady. So anyway, a nozzle, all this is it's a round tube. It basically it's a pipe that changes its diameter, and so they call it a nozzle. Okay, so to answer the question, what are you going to do? What I decided to do first was to use the mass rates. I'm going to write it as a rate because it's continuing to run constantly. So you don't really want to figure out how much mass went in because it's all going in at the same speed continuously. So anyway, the conservation of mass is here in the black. The mass that goes in minus the mass that goes out equals 0 because there's nothing changing inside inside the system, inside the nozzle. So nothing's changing. There's no mass that's added. And then I'm using the relationship between mass and area and velocities. So basically mass is equal to the density times area times velocity. Density is 1 over the little v, so that's why I'm dividing by the little v. So this right here is the mass in. This one right here is the mass out. So that's the red one is the black, putting it in terms of areas and velocities. The unknowns are the two green things I've circled. I don't know the exit velocity and I don't know the area of the exit. These guys in blue, I'm hoping I can look them up because I'm given temperatures and pressures on the in and the out. So I believe I can look those up. So you still have two unknowns. You need to do something. What are you going to do? What I wanted to do is to write the energy rate equation. So the energy that goes in, you have some mass going in on the left-hand side, the rate at which the mass goes in, just like these were rates up here. So that's the rate that mass goes in. In this case, the energy that goes in is internal U plus flow work. So that's H. So whenever you have U plus flow work, it's H. So this is the H that goes in. There's some kinetic energy going in because I have velocity, so I add the kinetic energy. This is energy that's leaving due to the heat transfer. If you notice, I'm writing it as 25,000 because those were kilowatts that was coming out. It's really, if you look real close, it's got a dot on it. It's trying to tell you it's a rate of this thing. So anyways, 25,000 because I'm using standard units. And then the energy that flows out is the amount of mass that flows out, and then the flow, the internal energy plus the flow energy, and then I have some kinetic energy also going out. That equals 0 because I'm not getting any more energy or any less energy inside the system. So that's the energy. Now, what it is I think I can look up the guys in blue, but I need to solve for the three things in green. So what is it that we need, right? Do we need something else, or can we just look things up? Give it some thought. Okay, we don't really need an equation, I guess. What I'm going to do is I'm going to take this piece right here and I'm going to set it equal to the mass in. So I guess you can count that as another equation. So the mass in is equal to the area times velocity. 1 over the volume is the density. So this is density times area times velocity, which we've seen before. Okay, so now I'm going to look up the values. Question is, what table? Saturated or superheated? See if you can find out. Well, to determine if it's superheated or saturated, usually I go to the saturated table. In this case, I'm going to the pressure saturated table. So this is table A5. The inlet is 800 kPa, which is the first row in this column. It would boil at 170 degrees centigrade, but it's going in at 400, so it's a lot hotter than the boiling temperature. So that would tell me that the thing is superheated. So I'll pull up the superheated tables, see if you can find the values. Okay, table A6 is the superheated water or steam. We have a pressure of 800 kPa, but the pressures here are in megapascals. So 800 kPa is 0.8 megapascals. And here's the table for 0.8 megapascals. The temperature on the inlet is 400. So we're looking at this column right here. And what I'm looking for, let me scroll where I can get that, 400. I'll put it at the bottom so it's easy to see it. Let's see, there we go. All right, so we're looking for the volume and we're looking for the H. So this is the volume, 0.384, and the H is the third column over here, which is 3267. All right, now watch the units on this thing because this is kilojoules. If you're going to use standard units, you want to put them in joules. So this would be 32,67700. Okay, so that's the inlet. Look up the exit as well. Give it some thought, see if you can find the values. The exit condition is 200 kPa, so that's 0.2 megapascals, and the temperature is 300 centigrade. And so we're at this point here. Here's your volume, 1.316. And the H that we're looking for is 3072. Again, watch out for the units on this thing. So those are your table lookup values. Okay, so now I've got the table lookup values here. And so now all I'm going to do is try to solve it. So I'm going to grab this piece. This is equal to the mass that flows in. So that's here. So the mass that flows in is equal to the A velocity over V. And you just plug the numbers that you're given in, and you find out that the mass that comes in is 2.081. And that the unit here would be standard units. So this would be kilograms per second. Now, according to this black one, the in is equal to the out. So I know that the outlet mass is equal to the same thing. Okay, so the next thing I'm going to do is try to solve for the volume flow rate out. See if you can do that as well. Okay, so what I did was I just took the same equation here for the inlet and I applied it for the outlet. So mass out times V out equals the volume flow out. So you just plug the numbers in and this is the volume flow rate. Okay, so the only thing left is to find the velocity. What I did was I took this final equation that I had right here, the energy equation, and the only thing that I don't know now is the velocity of the exit. So you know all of the numbers, you just plug in very carefully, just make sure that you use your calculator properly and calculate the exit velocity. So see if you can get that done. Okay, so the correct answer is 606. What are the units on this? I'm using standard units, so the velocity is in meters per second.